Hi, I'm Maria Jose and I'm going to present the convective mass transfer problem for the final project of transport processes 2. The description of the problem says that a group of chemists are working in the lab to develop a sanitizer for surfaces that contain chlorine. They apply a thin film coat of sanitizer over a flat surface that is 2 meters by 2 meters. And inside a rectangular draining chamber there is air circulating at a rate of 40 cubic meters per minute at 20 degrees Celsius and 1 atmosphere. The objective is to calculate the average convective mass transfer coefficient and the evaporation rate of the sanitizer from the surface in grams per minute. It's important to have the chamber measures that are shown in the drawing below, also the partial pressure of the sanitizer, and for the concentration calculations it's important to note that the concentration in the sanitizer vapor in the bulk gas is very small. Here we have the properties for both compounds. In table 1, the chlorine properties. It's important to say that solute A is the air and solvent B is the chlorine. In table 2, we have air properties. For both compounds, the properties were taken at 20 degrees Celsius. There were different approaches used to solve the problem. Some of them were the table of properties from the thermodynamics book called Schengel, also formulas and problems seen in class, knowledge gained from other subjects was applied also in this problem, and teamwork. Teamwork was very important to assure the correct results. So now for part A, here we have our general equation. After we're going to develop it more clearly, but here is our general equation. We only need to calculate the Sherwood number because we have the other values. So to calculate the Sherwood number, first we need to do the Schmidt number, and then the area of the chamber, so then it could be used in the velocity, and then the velocity will be used in the Reynolds number. Our flow was in cubic meters per minute, so it needed to be changed to cubic meters per second. It's important always to put the units so you can have a guide of the path you are taking. Here we have our Reynolds number. We can say that it's a laminar flow because the value obtained is smaller than 10 to the 5. Then we have our Sherwood equation. Because it was a laminar flow and is asking for an average value, we use the average laminar flow equation for the Sherwood number. And then also from the Sherwood equation we can clear out our Kc, that is the value that we want. And we obtain a value of 6.87 10 to the minus 4 meters per second. For part B, here we have our general equation. We already have our Kc, but we are missing the area of the sanitizer and the concentration in the surface. Because the concentration in the bulk gas was very small, we can delete it from the equation. And we have our general equation looking like this. So we have the area of the sanitizer, and then we calculate the concentration in the surface. Here we have our equation previously mentioned, and we we obtain a value of 0.02 mole per second. It is a molar value and we want it in mass units. So a simple conversion was applied where the molecular weight of the chlorine was used, and we obtain a value of 43.02 grams per minute. It can be concluded that the value of Kc indicates how fast is the mass transfer by convection. So with our result, it can be said that the system will be slow. Also, this method is viable because it gives you the properties of the fluid and also the geometry of the system. This method can be applied in design manufacture of separation process equipment and waste treatment processes. Some difficulties that we faced during this problem was that they give you two areas. So it's important to note which area corresponds to which calculation. So we make a relationship that when you calculate WA, that is the area of the sanitizer, is because this is the one that has the contact with the chamber or the metal. Also, some learnings were that the units and the diagram are really important to have a clearly idea of what you are looking for.